Hello. In this video, we're going to cover how to do hypothesis testing for difference of proportions. So this covers the exact same procedures in Lab 9A, except for instead of looking at one proportion, we're looking at two. So here's the picture of what's going on. We got one population, and we got another population. We want to know, is there a difference between these two groups? So here's sample one. This is what we do. We conduct two samples. And for each sample, we get a proportion. This is P1 is the proportion of successes for sample one. P2 is the proportion of successes for sample two. I'm going to know, is there a difference? And the way we test that is P1 different than P2? Is that the case? We would say H naught is P1 hat equals P2 hat. There is no difference, no difference. And if you think about the statement here, we could rewrite this as saying P1 minus P2 hat equals 0. Same statement. And so this is the test we're going to use. We're going to test that. H alternative would say, no, P1 is not equal to P2. And so that's what we're doing. Same process as if there's just one, but now we got two samples. We're looking at the comparison of them. So this is actually a more powerful test than what we did in the previous lab by finding different proportions for two different groups. I think this was actually lab 8, where we compared Trump and Biden's voting rates from a sample to see if there's a difference. And so, but the difference in this test is it requires us to have two different groups we're sampling from. So let's look at the conditions. To be able to do this analysis, we need to say that the difference of our two proportions, P1 hat minus P2 hat, if we were to sample many, many times and get these proportions, this distribution would be nearly normal if the data is independent from the two groups and it's within the two groups, independent within the two groups. So this means that between two samples within a group, I'm not having any correlation, and also there's no relationship between the two groups of who I pick. And so usually this is met when both are random samples. So the other condition, like before, is we need to have a large enough sample to say it's normal. So in this case, we need to have at least 10 successes, and 1 times P1. This P1 is the probability of success, or the proportion of success. So if we multiply that by our sample size, that gives us successes from the first group, N1 times 1 minus P2, that's the number of failures from the first group. That needs to be at least 10. And the same thing for both successes and failures of the second group. And then if these conditions are true, we got a new standard error. The standard error of this P1 minus 2, P2 that we're trying to sample looks like something like this. So that's the theory. This is what the central limit theorem tells us for two proportions. So let's look at an example. Here's a situation where you'd use a difference of proportions test. We got two groups, and we're saying, hey, what's the likelihood of different age groups voting? The people that are 18 to 24, looks like out of 100 people, 26 of them, or 26% of them recently voted. And of the second group, 100 people as well, higher age group, 29% voted. So you see here's our two groups. Group 1, Group 2. One group sampled 26%, another group sampled 29%. Is this difference significant? I really don't know without doing a test. And what I mean significant, is it more of a difference than you'd see when looking at random chance? So here's how we test that. First, we got to check the conditions for being nearly normal. So I want to find N1 times P1, N1 times 1 minus P1, and N2 times P2, and N2 times 1 minus P2. we can do this real fast as long as I specify what N1 and N2 and P1 and P2 are. So based off our data, we had a 26% people voting in the first group. N2 was also 100. P2 was 29%. So these are the two proportions that we want to compare. And so to see if the conditions are satisfied, let's run this. Well, we had 26 successes with the first group, 29 successes in the second group, and their failures, of course, are going to be big enough as well. So they're satisfied. Look, oops, looks like I didn't need to type that out. Anyhow, you can use what I have written there if you want. So now, let's take the pooled standard error. This is the standard error of our sampling distribution. Actually, we don't need to call it the pooled standard error. It's just the standard error of P1 minus P2. So this is actually the variance, P1, 1 minus P1 divided by N1. That's the variance of the first group. I add it to the variance of the second group. And then I divide, or take the square root to get the standard deviation, standard error, the standard deviation of my sampling distribution. So what does that give us? That gives us all the information we need to find our confidence interval. The confidence interval for the difference of two proportions is the difference itself plus or minus some critical value times SE. Remember that critical value? Z for the 95% confidence interval, Z star is 1.96. So that's what we use for this first problem. So here's just the information again to remind us we're trying to test the difference of these two percentages. So we would say P1 minus P2, since I've already saved those correctly above, and I haven't done anything else in between, I can just say that. And I say plus 1.96 times SE, because I've already found the SE right directly above. These should be accurate now. So that's the upper bound, and this is the lower bound. So let's look at our interval. Here's the information. This is our 95% confidence interval for the difference of proportions of people voting. You could say ages 18 to 24 versus ages 25 to 32. Okay, so we've got to put this in context. We've got two different people voting. Is there a difference? Here's what our confidence interval says. It's negative 0.07, I'll say 79, up to 0.019. Okay, that's our confidence interval. Now, what does it tell us? Oh, I should have put this above here. This should be here. So what does the confidence interval indicate? Well, since 0 is in our confidence interval, P1 minus P2 is plausible. Equals 0 is a plausible result, I should say. So it means we don't know there's any difference. 0 means no difference. So we should really say there's no evidence. There could be a difference still, statistically significant difference, but we don't see one here in this size of a sample. So that's what it tells us. So statistically, we know that based off the sample size, there's no evidence that there's a difference. That's what we can do from this. Okay, so that's the first way to interpret our hypothesis test, is with a confidence interval. Next, let's do the p-value. So the p-value, we need to really say what our hypotheses are. So I'm going to skip down to question 5. The hypothesis are that P1 minus P2 is 0. Difference of the two groups of 2 is 0. And remember, that's the same thing as saying they're equal. The two groups are equal. And if we say P1 minus P2 is not 0, that shows me that there is a difference. So how do we go about testing this? Well, firstly, when we do p-value, we assume the null hypothesis is true. We assume this is the case, and then we gather evidence to either reject or fail to reject it. So to do that, we actually have an updated standard error. Because these are equal, we have to actually calculate a standard error using all the information we have, which adds up all the successes and divides by all the number of cases to get the total proportion of two groups. So it's called the pool proportion. So let's first find that. Let's find the pool proportion. So the pool proportion says N1 times P1. That's the number of successes from the first group, times N2 times P2. That's the number of successes from the second group. And we're going to divide that by the total, N1 plus N2. And just to be careful, when I'm doing this, I should always make sure I have the correct values for these things. N2, P2. I'm just going to put these here, even though we might already have them. This will save us making mistakes later if we're using incorrect values. So here we go. Here are the values. Here's our new proportion. I'm going to tell you it's going to be something in between these two. It's like we're taking the average of these two proportions between the two groups. So 27.5. That's the proportion we're assuming for which we're going to make our new standard error. So what's the standard error here? These are all things we need really for finding the p-value. So the standard error is this formula here. Square root of pp. Oh, I'm going to call this thing pp for pool proportion. I'm going to run that again to make sure I have pp written in here. Okay. And here, just so I can see it still exists. Okay. This is pp times 1 minus the pool proportion divided by n1 plus pp times 1 minus the proportion divided by n2. This is our new formula for the standard error. This is the only thing that changes, these two parts. So once I find my standard error, this tells me, hey, I know the distribution of my sample. So so the distribution of P1 minus P2, it's distributed. This is what we're testing, the difference. It's distributed normal, 0, because the mean is going to be 0, and this thing's my standard error. So please don't stop once you find the standard error. That just tells us my distribution. This tells me, here's the shape of what I sampled from. It's got a 0 center. The standard error is something like 0.06. And what do I observe? We got to use this to say something about what we observed. We observed P1 minus P2 is a negative 3% difference. So we observe something that's over here. Get my drawing in order. Negative 0.03. Okay. Now we got to find out what's the probability of getting something more extreme than that. That's what our p-value is. So we got to find, there's a possibility that 0.03 is to the left, or so this number or less. But we also have to consider maybe that number could have been equally far to the right. So we have to find the upper and lower tails of this value. So that'd be 0.03 to the right. So to find this, we got to say lower tail is p norm of that difference, P1 minus P2, which is negative 0. Say negative 0.030. I'll just put SE in here. No, I'll be safe. I'll put that in here. So that's lower tail probability. And what I actually need to do, I want to double this times 2 to get both tails. It's called the two-sided hypothesis. So once I double that, this tells me P equals 0.63. So since this p-value is getting so large, we do not have evidence to reject the null. There is no difference. So the null is plausible. There may be a difference. There may be no significant. I should say there appears to be no significant difference. Okay, there you go. That's it. That's the two-sided test in all its glory. Now you guys can follow these exact same steps to answer the following 3 problems. And I highly encourage you to try to do this on your own. If you can see it once and do it once, you are practicing good understanding of the concepts. If not, note the textbook goes through the process in section 6.2.2 up to 6.2.3. And so you can check your work that way. And I think, yeah, I'm going to let you go on that. If you have any questions, please come to class. Please ask everything that you're doing in this class. Once you've tried and gotten stuck, that's where I really want to help you. But you do have to put forth the effort. You have to work hard. I will work hard for you as long as you're working hard yourself. All right. So again, once you get to the end of these 3 problems, please check your own work. You can check those answers. Even if they don't have both the confidence interval and the p-value, whatever solution the textbook provides you should agree with your other solution. So whether you accept or reject the null should be consistent for all 3 of these problems. All right. That's all. We'll see you in class.